Sure.
All right, welcome everybody to today's Physics Meets ML. We're very happy to have Ge Yang here. He is currently at the NSF Institute of AI and Fundamental Interactions. He's a postdoc there at MIT. He did his bachelor at Yale and his PhD from University of Chicago. He also visited Berkeley, and he did research internships at DeepMind, Facebook, and Uber. So we're very happy to have him and tell us about his research. Please go ahead.
Oh yeah, thanks. Yeah, sorry. Like when Jim told me to give a presentation, I was expecting something like a little bit less formal. This is also like a brand new talk that's that I'm kind of developing as kind of like a roadmap thing for what I want to do like afterward. So like there's a lot of kind of like related works where I get like a little intuitions from. That's just kind of like put together still in the fairly loose form. So I hope you guys bear with me. And feel free to actually like raise your hand or like interrupt and like ask questions. Okay. All right. So my name's Ge, and today I'm going to talk about some of my thoughts on like basically equivariant neural fields, like a roadmap towards generalizable neural representations and inference. It's going to be a mix of like some kind of like review and some of like a review of my own work and like some projections to like what are the good next steps to do like in this direction. Okay, so the talk is arranged this way. So first, I want to like talk about like why we want to actually look at like learning and generalization, and why like a kind of like symmetry and equivariance is kind of important, and like what kind of gain do you get. And then the second part is going to be like what type of problem I'm interested in like tackling specifically, like the problem domains. And then I'll talk a little bit about methodology, where like I took inspiration from like previous works. And then finally, like a very quick and sweet, like a roadmap on like things, what I think we could do next. Okay, so why like a generalization? I've been interested in this problem for a while, and I think like in the end, like learning is basically just counting. It's a glorified version of counting, and the way that we parameterize neural networks, it affects how we aggregate data into like weights or parameters. And it also affects whether we can find those solutions quickly. So that's kind of like the learning aspect of the learning and generalization dual. So in this figure, for example, I took like one of the figures from one of our recent papers. And here in blue is like the learning curve for one of our reinforcement learning agents. The vertical axis is the success rate. And if we compare basically like the learning curve from these two agents trained using the same like reinforcement learning algorithm, and the only difference between them is just how we parameterize the neural network, then there's actually a gap. So this type of gap, in terms of like differences in like how quickly like they learn, is the type of gain like I'm looking for. And I think by actually reparameterizing our network specifically for the like a new like a data domain or data types, we might be able to like produce this type of like a performance or learning gains because we're better at aggregating like data into knowledge, and we can find it quickly. So one inspiration for like this, let's see, okay. So like on the second point, whether we can find it quickly, I want to like basically briefly go over one of our recent work. It's called Overcoming the Spectral Bias of Neural Value Estimation. This is a reinforcement learning paper where we specifically look at the intrinsic learning biases within the deep neural networks we commonly use. In this case, it's a multi-layer perceptron. So consider like the reinforcement learning of finding like a policy. In this case, we have a very simple like toy MDP problem where the state space is between 0 and 1. An action space is a set of like two actions. We indicate them by like 0 and 1. And the reward is basically proportional to like the state where the agent is in. So it's a very simple dynamics where for each one of the two actions, there's like a piecewise linear dynamics where that we define arbitrarily. Here it's not Newtonian like mechanics. It's important to like know that it's not like a little mass moving under a force. It's basically just some random like next state transition that we define like in this very artificial environment. And if you actually use like a value iteration to calculate the ground truth, like a value function for this very simple neural network, what you get is the following. You get like this fairly complex Q function that's like a lot more complicated than this very simple like a piecewise linear like a MDP that we begin with. And this example is actually taken from this work from Dong et al. 2001, where they investigate the complexity of like a value learning in model-free reinforcement learning. And their claim is because learning a value function is so difficult, you shouldn't learn a value function, but instead you should like do model-based reinforcement learning or do like model-based planning so that you don't actually have to like try to like approximate such a complex Q function. And like in this case, notably, these very complex Q functions actually have a lot of high frequency components, which shows up as these basically little spurious peaks in the ground truth like value function. So here, the two colors like corresponds to the Q function that corresponds to each one of the actions, because the Q function is also parameterized by the action. So there are actually like two Q functions for this like a MDP with the discrete action space of two actions. So their claim is that like basically like you shouldn't actually try to learn value function approximators because it's challenging. And so we did a very simple experiment. So like here's the complex value function we're trying to approximate with a lot of high frequency components. Now, if I use fit acute iteration, which is like an offline like Q learning method, to actually try to like basically calculate the Q function from like transition like tuples, then you get like something like this. In this figure, like I'm plotting basically the Q function for the two actions in the same plot, the same way that I plotted like the ground truth Q function. You can see that the fit is extremely poor. It doesn't like, it resembles basically the overall shape, but like it kind of misses not just on the details, but like all of the decision boundaries are wrong too. So the question is, so like is the like a fit acute iteration producing these bad results simply because like we're not giving enough data, or we're not giving enough like, you know, like, or maybe it's because like the Q learning method is broken. Like we know that basically like reinforcement learning algorithms can be very complex and they're also unstable. So the question is like, are we getting bad value approximators because Q learning didn't work or because something else? So here we did a very simple control experiment where instead of using Q learning to learn this value approximator, instead we use a supervised learning. So we take the ground truth value function from the left, and then we use supervised learning to regress towards that. And after 400 epochs, 400 learning epochs, the neural network is actually unable to fit to the complex Q function we have on the left. And then like you're like, actually, like this is because the neural network is not complex enough. Like, can we just make the neural network bigger or wider? So we did that. We made a 12-layer multi-layer perceptron that's also like learned via supervised learning after 400 epochs. It also produces like a pretty bad approximation of the ground truth value function. And now you ask me like, but neural networks are supposed to fit any functions, right? There are theorems that proves that, the universality theorem. And it turned out the issue is not the expressivity of the neural network, but how long it takes for the neural network to fit to this Q function to the left. So it takes like 2,000 epochs. And on my like computer running on the CPU, this takes about like, I think like 30 or 40 minutes. So like the neural network is only able to fit to the Q function if you run it for a relatively long time. So here you can see that the Q function is still missing important details of the the function approximator is still missing important details, but it roughly like kind of fits the overall like landscape. So the reason why this happens is because one of their perceptrons have a special bias towards low frequency functions. So what it means is that it takes exponentially more gradient updates in order for the multilayer perceptron to actually fit to these high frequency components. So this is why I want to talk about the optimization and learning angle as well, besides like a generalization. So this happens, because this is looking at things like through the lens of looking at a reinforcement learning problem, we kind of wanted to actually look at the problem a little bit more carefully. So here we did some spectral analysis of the value approximation problem. So in reinforcement learning, you have the Bellman equation. In the Bellman equation, there's this operator B called the Bellman optimality operator. That's actually defined here. So the Bellman optimality operator takes a Q function and expresses the Q function in terms of the next step reward, the one-step reward, and the maximum Q value for the next step. So what a fit Q iteration or a Q iteration is that you basically apply this Bellman operator on top of each one of the Q functions recurrently, and then it produces a sequence of Q functions, each one of them with an additional application of the Bellman operator. So by actually recursively applying the Bellman operator onto the Q value function, you actually go from the simple dynamics we have on the left to something fairly complex to the right. So the first step of the of the process is to apply Bellman operator to the reward function, and then after a few steps, the Q function becomes fairly complex. We can look at the complexity of Q function from the a spectrum angle. So here I'm taking the a discrete a Fourier spectrum of the reward function. In this case, I'm using a reward function that's basically a single sinusoidal function to keep it to make sure that the spectrum is relatively clean. The roll-off you see here is not due to the reward function itself, but instead it's actually due to the windowing effect of a finite sampling window. So this is actually the spectrum of a square a box function. It's an artifact. And then if you apply the Bellman optimality operator to the Q function once, you basically get the second Q, and you can see that the spectrum kind of lifts off to have a bigger component in the high frequency part of the spectrum. And you can apply the Bellman equation onto the second Q again to produce Q3 and then Q4, so on and so forth. And you can even do this by actually applying the same number of same number of times, but just change the discount factor. You basically produce almost exactly same effect. Whereas by actually increasing the number of a Bellman operator's application, or by increasing basically the expected time horizon of the Markov decision process, the Q function becomes more and more complex and have a bigger and bigger component in the higher frequency part of the spectrum. So the reason why value approximation in a model-free reinforcement learning is challenging, it's because of this a kind of recursive structure where the spectrum of the Bellman operator gets imprinted onto basically the reward function. And notably, the Bellman operator includes the Markov decision processes for dynamics, which is why its spectrum is so complicated. So now we know why, in reinforcement learning, we have a little bit more challenging function approximation problem than supervised learning, where people believe that the reason why deep neural networks generalize well is because all of the answers lives on a low energy and sort of a simpler hypothesis, kind of manifold. Let's see. To answer the question, does the fit depend on hyperparameters such as learning rate In that case, it does not. Learning rate is hyperparameters that we tweak a little bit, but not too much at all. So it doesn't matter because learning rate it doesn't depend on learning rate. So this is for a fixed learning rate at a higher frequency, it learns much slower. Okay, so the deep learning theory community has offered very good toolings for understanding this type of problems. Notably, we use the tool of neural tangent kernels, and we're inspired by a recent developments in the graphics community where they use these random Fourier features to allow a very simple multilayer perceptron to learn a very high frequency image representation, image functions in low dimensional coordinate spaces. In this case, basically we can treat under this from this perspective, you can basically treat any neural network that's learned using gradient descent as a kernel function, and its learning its learning rate. It's basically depends exponentially on this kind of a special component of its kernel, and one neural tangent kernel is it's basically defined as the a kernel is defined as the the cross product between the first order gradient of the neural network taken with respect to two data points. So the kernel functions evaluate over two data points, xi and xj, and the way that you compute the kernel is by taking first order derivative through the neural network as a function, which is basically the gradient vector, and the gradient vector is a gradient vector that has the same rank as the a parameter tensors. So it's basically a bunch of tensors put together in a tuple, and then if you flatten all of these together and calculate the dot product between the two of them, this gives you a kernel matrix, and this is called a neural tangent kernel. So you can very easily reproduce this using PyTorch, but just numerically, calculating the gradient vector flattened for a bunch of data points between 0 and 1, and that's how I generated the plots you're going to see next. And the important thing here is that the spectrum of this kernel matrix determines the convergence of the network under gradient updates. So to respond to the question earlier, it does depend on the learning rate, but the relative rates between the different components does not depend on the learning rate. And in fact, most of us just use kind of a learning rates from a very small range, because larger learning steps will actually cause things to crash. So here, by just calculating this numerically, you can actually produce a visualization of this kernel matrix for a multilayer perceptron with a rectified linear unit as the activation. And you can also do this for MLP with the hyperbolic tangent activations, which is something that a lot of reinforcement learning algorithms use because it's a little bit smoother in terms of its output. You can also do this for a dense net, which is one network that's specifically proposed to address the problem of a lack of expressivity, or a neural networks or policies or value functions not having enough expressivity, being the main bottleneck for not getting better performance in deep reinforcement learning. You can see that if you look at the neural tangent kernels of all of these three networks, they look roughly similar in the sense that they're very broad. And in this case, we introduce a one-line change to the multi-layer perceptron, which produces a completely different neural tangent kernels. So on the left, we have the a PyTorch code for how we define the Q function using the multi-layer perceptron. And if we just replace the first layer, which is the linear layer plus the ReLU nonlinearity with the random Fourier feature layer, then it's actually able to produce a Q function approximator that almost exactly reproduces the ground truth Q function. And this drastic change in the basically empirical result can actually be explained by neurotangent kernel theory. So we can also visualize the neurotangent kernel of the like a multilayer perceptron with one layer of a random Fourier feature. What you see is that the neurotangent kernel has like two different properties. The first property that's different is that this neurotangent kernel is a lot narrower. What this means is that there's a lot less crosstalk between like data points that are next to each other. So in this kernel matrix, each one of the axes is basically an axis for the input for the input of the network. So the input of the network is between like a minus 0.5 to plus from minus 0.5 to plus 0.5. And the same thing is repeated on the other side because it's a kernel matrix. So it's like so this much like a sort of like a narrower, like a diagonal, like a feature means that there's almost like no crosstalk when you actually update the value, the Q value for one state versus another. This means that like a value of function approximator almost resembles a tabular like a Q function. Like it basically resembles a table because a table has zero crosstalk between the nearby states, whereas like a neural networks has a lot of like crosstalk between nearby states when you use gradient to update it, which is why like in this case like a fitted curation almost like completely fails to fit the ground truth Q function. A second feature is that this yeah, go ahead.
Yeah, hi. Just a quick question. How good a approximation is the MTK and this for these networks? So does it...
Oh, I see. So in this case, I compared the analytical calculation of NTK with the numerical. In this case, I'm using kind of like a 4-layer neural network. I didn't I didn't notice like too big of a difference. So like basically for all of the visualization and calculations, I just ended up just like calculating all of these NTKs numerically.
I see. Yeah. Okay.
Yeah.
Thanks.
Yep. Okay. So now with like this kind of understanding of like what is happening here, we also realize that by actually changing how we actually randomly initialize the weights for the random Fourier feature layer, we can actually also tune the half width, half maximum bandwidth of the neurotangent kernels to actually control how much crosstalk or generalization we get when the agent try to approximate the value function. So in this case, I basically try to reproduce I basically try to plot the spectrum of the kernel and the kernel itself for basically different random initializations of this weight matrix W here. So here the letter B actually it's actually represents the amplitude of this random weight matrix W. I can see that basically by making W bigger, you get basically a sharper and sharper kernel, which start to have all of these high frequency components in the spectral domain. So two things are kind of important here. The first thing is that it's important in high dimensions to actually initialize this weight matrix in an isotropic way, because in a lot of implementations we've seen in the field, they're using uniform initialization, which is actually initializing inside inside a hypercube. So it's actually not isotropic along all of the different directions. So we noticed that. Yeah, and then the second thing is that the number for your features grows almost linearly with respect to the input dimensionality. So in all of the prior works, they were mostly concerned about a very low dimensional input spaces. For example, a 3-dimensional coordinate system for nerve. But in reinforcement learning, we need to in a lot of the domains, we actually have like all the way up to like, 300 dimensions as basically input state space with like a little bit smaller number of like action spaces. And like these two things need to be concatenated together like as input to the Q function. So like in reinforcement learning, we're actually facing like a drastically different dimensionality from these like a coordinate-based neural networks that people use in computer graphics. And because of that, we actually had to fix one of the issues that we have seen like in prior works, which is we have to like figure out like a good way to initialize the random weight matrix in a way that is actually dimensionally agnostic. So like what I mean is that like you actually need to rescale the weight matrix so that like the sum of each one of the rows actually like a relatively it's controlled directly by this basically like a scaling factor B, as opposed to basically let like these like scaling factors actually depend on the input dimensionality. In our case, because we typically evaluate our like reinforcement learning agent across like many different like we use the same learning algorithm across and the same like architecture across like many different reinforcement learning domains in the same like a benchmark suite. Each one of the domains will have like complete different like dimensionality to their state and action spaces. So we're looking for a way to initialize these like weight matrices that is actually like dimensionally agnostic. So in the end, what we did was that we just kind of like we used basically like we use the input dimensionality to scale the weight matrix so that like the random features have like roughly the same like norm. To answer the question, like the question is, can I explain the change that enabled me to like fit the curve? I did a random initialization linear layer in the middle, which is not trainable. Okay, let me clarify that a little bit. So basically, like you have a typical neural network. The input is basically the state, and the output is like the Q value. And this is how you implement that. But then you take this like a first layer, which is a linear layer plus like a rectified linear unit. You replace that with a random Fourier feature layer, which is basically a linear layer plus a sinusoidal activation function. So the only thing that changed, besides we don't train these random features, is that we use a sinusoidal activation function. But then we start training these values because we realized that even though it worked for a lot of people that they don't train these like weights, if you actually reduce the number of layers to 2 to 3, the number of parameters contained in these like a random Fourier feature layers is actually substantial enough that like not training those parameters actually affects like basically the expressivity of your network. So in the end, for these extremely shallow networks that are only like 3 layers, we start to train them end to end. But even though you can train it, it's still extremely important to actually initialize them into the right ballpark, because the activation is periodic. So gradient descent cannot get them out of basically a small vicinity. So gradient descent actually doesn't affect the the norm of the like a random matrix too significantly, although it does change it in the statistical significant manner, which you can evaluate. Yeah. So basically for larger networks, you don't have to train it, but like it's better if you train it. Even if you train it, you still have to initialize it correctly. And we fixed basically like initialization bug in prior works to make it basically agnostic to number of input dimensions. And you get that. Okay. All right. So here's like our like and here I wanted to do something nice. So I took like a mountain car, which is this 2-dimensional like a Markov decision process. Because the state space is 2-dimensional. So mountain car is basically this little car that tried to like drive to the top of the mountains under actuated. So it doesn't have enough like force to drive itself up. It will just like slip down. So in order to go up, you have to do a parametric amplification, right? So you have to like swing the swing to go up. So that's mountain car. The state space is one-dimensional because it's just position. Sorry, the state space is two-dimensional because it's the position plus the momentum. So those are the two axes. So here the like a value like we show by like a black and white is the it's the Q value. There are actually 3 Q values because the action space is the 3-dimensional. It's a discrete set of 3 actions. But I'm just like plotting one of them so that it's easier to see. So you can actually do like fit a Q iteration on this on mountain car using like Fourier MLP. Like after like some number of iterations, you get basically like something like this. I think I used either 2000 or something like that. It should be somewhere in the paper. And then like if you use like again a deeper MLP, you get like a little better performance, a little bit better fit, but still like it's pretty fuzzy. Again, you can use MLP plus hyperbolic tangent. And it looks basically like a very smooth, but like much more fuzzy, right? And then like you can compare ours, which basically replicates like all of the details in the in the ground truth like value function by running the same like fit Q iteration as the other baselines. And this experiment is really quick. It takes like 15 minutes to run, so like it's really nice. It's like a small tabletop experiment. Okay, so now it's time to scale it up. So we implemented like a random Fourier features. So we call like the fixed version the RFF MLP, and then we call the like a learned version the LFF MLP. And this is actually like some old data I had. Like we have even better results than this one now. So in this case, you can see like basically the self-articulated baseline on these like a DeepMind like a control suite task, quadruped walk and quadruped run. Does like a kind of okay-ish. These are actually state-of-the-art performance like in state space DeepMind control suite. And then like if you just add like our one layer of like a random Fourier features and like we just kind of like blow them out of water. And you can actually run the same experiment across all of the domains. So we do this on like 8 different DeepMind control domains, and you pretty much just like do better in like in most of the circumstances. So this is kind of like the scaled up version of basically applying like random Fourier features and learned random Fourier features or learned Fourier features to these kind of like high dimensional large scale reinforcement learning problems. But what we also found during our like a tabletop experiment is that even though like here we're able to produce like a very good like a functional fits to the Q function, if you actually overlay this fitted like a Q value, like a Q function that we approximate on top of the ground truth value function, there's actually a noticeable offset. So as it turned out, like in Q learning, because you have a target function, so you're actually just learning the finite difference between the of the Q function between 2 states. So like you're only like basically like supervising the Q function using its derivative. So like the Q value can actually have like a constant offset that's actually underdetermined. So yeah, if I actually overlay this learned fitted Q function on top of the ground truth Q function, there's actually a very large gap. So we thought that actually, if this is the problem, maybe we can even get rid of the target function, because the target functions only exists to stabilize the like a Q learning process, so that the right hand side of the like of the sample-based Bellman like of TD learning is actually like more stable. So you're using target function to slow down the changes of the like a value target that you regress towards, and that the reason why you want to do that is exactly because when you push the value like for one state or one action down, it affects the Q value of another state, another action. And if we remove this crosstalk between state and action pairs, then like we actually most likely don't need the target function to stabilize learning anymore. So we ran that experiment, and it was really quick. It only took us like 3 days from start to like finish. And we realized that we can even get better performance like without a target network on a few domains compared to basically like using a target network. So this is why this paper is called basically overcoming the spectral bias of a value, like neural value approximation, is that in the past, in model-free reinforcement learning, people have developed all of these different methods to stabilize Q learning so that the crappy like a MLP, like a functional approximator, can actually work under this kind of like fitted queue iteration paradigm. But we found that actually making a single line change to the function approximator class itself, you're actually able to throw away a lot of those tricks, just because each one of the like gradient updates is a lot more effective at basically producing a better functional fit. So this is actually the optimization learning like angle to basically like making like improving like learning and generalization, in that you can actually make good solutions a lot more accessible for a fixed number of gradient updates. So to answer your Slav's like a question, what is tabletop? Oh, I'm using like a DeepMind control suite. So like I think a lot of folks are like, so we actually did this both on, so like there's the gym environment. So the stick figures in gym are typically called like Majoko environments, because that's what they were called to begin with. And then like DeepMind had like DeepMind control suite. So DeepMind control suites like rewards are much better calibrated. So and it's also like it was used extensively for like a pixel based like a model for reinforcement learning. So now most of these benchmarks are done on like DeepMind control suite. But we also have results on like basically the gym and Majoko environments, and those tend to be a little more difficult basically. But their reward is not calibrated, so like it's a little bit like a difficult. It's just going to be like 40,000 or something like that. But here everything's kind of like close to 1,000, so it's easier to compare basically. Yeah. Yeah, thanks. So the gym OpenAI, those are actually the Majoko environments, and then we have a DeepMind control suite. It's here. Yeah. Like I wouldn't call it data processing. I feel like I'll look if Thomas, I think it's a way to introduce like sparsification, in the data representation. I'll leave it like that. Yeah. Oh, I see. That's a good question. So I'm not sure about that actually. So
can you actually read out the question so that it's on the recording? Because the chat.
Oh yeah, sure. Sorry about that. Okay, cool. Yeah. So Thomas's question is that is the RFF layer, can it be viewed as a form of data processing? So if you look at like the literature, people from Brown, they had these. There's one called Fourier feature, deep reinforcement, Fourier feature reinforcement learning. So people were using these Fourier features as basically state features, like very early on, which is kind of funny. Like that paper's from like I think 2005 or it's pretty old. So people view these are really like features. They're not like data processing. Yeah. They're certainly different from data augmentation. Yeah. Darshil's question, is there a trade-off in using random Fourier features to better fit high frequency data? Do you have an explanation for why in some of these results random Fourier features perform slightly worse? We have some intuitions of why it performs slightly worse, but we're still investigating them. In terms of fitting high frequency data, I'm going to get into basically the trade-off between working the spectral domain versus working the position or space domain later on in this talk. But basically the take home is that for all of your regression tasks, you should use learn Fourier features. For anything you do, even in physics, when we do regression, you should use Fourier features. And if the input state is very big, you normalize it. If you have a lot of things going on, then you can use wavelet transforms. But you should always use these features to because otherwise, the neural network will just learn very slowly. Okay, so this is just a kind of segue. And one thing that's important to note is that in reinforcement learning, whether you learn quickly actually has a compounding effect. So basically, if you fail to learn quickly, so here we have the two baselines, right? One baseline is basically one of the neural networks that we reparameterize that actually learns much faster for the same number gradient updates. This is from a different paper, by the way. And we have the multilayer perceptron baseline on the bottom. if you actually like reparameterize this network in a way that's like not so good, which is another baseline, I just call it wrong in this case, the learning just completely crashes. This is because if like the speed, the progress at which the neural network learns is lower than a certain threshold, the kind of like variance and noise in the reinforcement learning process will just kill you. This is why in reinforcement learning it's particularly important to have basically gradient-based learning methods and procedures that are very fast. So in our case, we're effectively running we're effectively producing like a good updated Q-value estimates, which is a handful of like gradient updates. So if you calculate how many gradient updates we do, okay, so that was kind of like the why I want to do this, and I want to like kind of like get into like a little bit like a more ambitious part, and I'll just kind of race through these because a lot of these are just kind of like a literature review and conjectures to kind of like point towards like what I think is important to work on next. So let's first take a look at the problem a little bit. So I spent a lot of time thinking about how we represent information inside neural networks. And I started thinking about this as basically data types, as basically representations of some data. So typically when you look at like geometrical deep learning, people talk about graphs or like, like grids of like pixels on the grid. That's kind of what we work with in like revision, right? And then you have like these manifolds, which are like a sort of thin shells embedded in the Euclidean space. So like, people usually think about these as basically like a disconnected different like types of data, but in fact you can actually go in between them very easily. For example, in one of my previous work called like plan-to-vec and supervised representation learning by latent plans, we basically build up graphs on top of by collecting trajectories from a reinforcement learning agent, and then basically run multi-dimensional scaling algorithms, basically embedding algorithms on top of this graph that we construct using like some kind of like a local metric. So here you can actually go from like trajectory data to graphs. Also, like you can also like go from like images, which is kind of like pixels on the regular grid, to graphs as well. In this case, like I can actually like view the image as basically like a dense graph that's kind of like a connected neighbor-wise, right? But then like as soon as you start looking at things as graphs, you can also have sparse graphs where you work with these kind of like super pixels that are kind of aggregates like information from multiple nearby pixels. So the point I'm trying to make here is that in computer vision and in like reinforcement learning from like pixel inputs, we're kind of used to just like taking the images and then just process that using like a convolutional neural network. But like there are actually a lot of different ways to look at these data that contains the same type of information. And actually by looking at these data differently, you can use different tools. And like one thing I'm trying to get at today is that maybe we should actually look at these things that lives on discrete grids or like a discrete like graphs as basically discretization of some kind of continuous like a field, and the neural representation of these like fields that lives on a continuous like a manifold can be called like a neural fields. So like what is also like this kind of like framework of like looking at these different data types also gives us a way to actually see what is kind of missing. So my claim here is that we have the graphs that are discrete, we have grids that are kind of dense and discrete, and we have the manifolds that are kind of continuous, but they kind of just like lives on a thin shell. So in between, we actually have like these like vector fields defined on like some kind of like a metric space. So my claim here is that I think we should actually look at these kind of like dense descriptor, like basically like a neural representations of some of these informations, basically dense descriptor fields that are basically like vector fields defined densely in some kind of like a vector space. So the difference between this and like manifolds is that it's not necessarily on the shell. And then like the difference between this and the graphs and grids is that like it's continuous instead of discrete. And I think like focusing on like a specific domain data type is very crucial for making progress, because these domains do contain like constraints and intuitive biases that drives progress. So I want to just quickly go through like the history of Real Sense. It's a company that that did like facial recognition that was started by Michael Bronstein. They built this kind of like they were trying to basically like do facial recognition. So that was basically their task. But it turned out that like the image sensors that can actually give you like 3D data was extremely expensive at that point. So they actually had to build their own image sensor using like structured light. So basically structured light works by projecting these patterns onto like a 3D shape. And then you can actually back out the 3D geometry by basically looking at like where these lines are. And there's a different company called like Prime Sense that got like that was like responsible for Kinect, made by Microsoft, and that was later bought by Apple, which actually lives in your iPhone. So those are coded light, which is a form of structured light that uses basically lighting, like encoding directly in the light pattern to make it easy for the algorithm to like figure out which patch comes from like which part of the like which ray. And like basically like the developments in these like sensors has undergone like a huge shift in the past like 10, 15 years. And now like every iPhone since like the iPhone X has one of these sensors built in. And actually the iPhone X, when I just looked it up, has been sold like a 63 million like units. So basically, if you're looking at like if you're looking for the like ImageNet challenge kind of like a moment where the explosion of like a cell phone like images and on the internet like drove one of the biggest breakthroughs in like the deep learning history, then I would claim that basically we should be ready to look at like these kind of 3D data, or in this case specific point cloud data, because these devices are becoming like have become ubiquitous, and it's only a matter of time when like this type of data becomes something that we will be spending a lot of time like looking at and working with. So specifically in robotics, most of the cutting edge like results are using a point cloud data one way or another. A lot of them don't use this directly as the input to basically the visual motor control policy, but a lot of them use 3D point cloud data from one of these like prime sense or real sense like sensors to reconstruct some kind of like a orthonormal height map. For example, in local motion, like that's height map for defining the terrain of the ground, and grasping and manipulation is for defining the geometry of the object you're trying to interact with. And in this case, we have this MIT cheetah using a LiDAR to actually like try to tell like the terrain in front of it and trying to jump across these obstacles at very high speeds. And physics is also relevant. So I couldn't get a nice picture. So like here's basically like one of the galaxy density pictures from the like a dark energy survey. So like we have like collider data that are basically traces of particles going through the sensors. So my claim is that we need to figure out good ways to work with these new data types. And the way to do it is by actually re-engineering our neural function approximators so that its internal representation of these data actually respects like a rotational and translation equivariance. So because I'm a little bit short on time, I'm going to like basically try to pick the parts that's kind of like more interesting. So I'll basically just go here. Yeah, okay. Okay, I'm actually done with this part. Okay, so we talk about the problem we're trying to solve. What are the solutions people have come up with like so far? So there's this big division between spectral methods versus pattern matching. So you can think about spectral methods as basically working in the spectral domain, whereas like pattern matching works in the space domains. And what's in between is basically like wavelet, which kind of does a kind of like uncertainty trade-off between how precisely you measure like the spectrum of some signals versus you measure like basically like the time, like the spatial localization of those signals. It's kind of like similar to uncertainty principle, where you have like you can either model like basically the position precisely by actually doing pattern matching, but then you lose the like a lot of the spectral like information because you have this finite like sampling window. Or you can actually do like what we did, which is kind of like modeling everything using like Fourier spectrums, but then like it doesn't actually matter for the features like where you are like position wise. So these are the trade-offs. So there's like a very large line of work in like a geometrical deep learning that kind of like treats basically like these manifolds as graphs, and we know that basically like you can extend like Fourier functions, which is the eigenfunctions of a second order derivative like operator on like basically one dimension and like Euclidean spaces, right? Like what geometrists like to do is that they extend things to like non-Euclidean manifolds, and they extend things like from one dimension to higher dimensions, right? So if you just do that, you got like basically the graph Laplace, like the Laplacian operator. And then if you actually do that on the graph, then you basically get like basically the graph Laplacian, which gives you basically these eigenmodes for each individual graph, and that gives you basically this energy scalar that allows you to like rank them like more or less. So the problem with using graph Laplacian is that the graph Laplacian is intrinsic to each one of the manifold, which basically means that the eigenmodes is different for each graph. So for example, here we have a horse running around. The two images on the left are identical, and the one on the right is actually from a different pose. So like the small changes between the left two images and the one on the right is that like the lag pose changed ever so slightly. So if I train like basically a feature like a predictor on basically like these kind of red patches, it's trained to basically regress these red patches on the horse on the left, and then like basically plot the principal components on the right. You basically see that like it's completely crap. So this is the problem with using like a graph Laplacian methods and working in the spectral domain as opposed to working in the space domain. And the way that basically people in the like a geometric deep learning like a field solve this problem is by like basically adding like a localization. What that basically means is that they're just basically doing what convolutional neural network does, is applying like a pattern matching to the manifold piece by piece. So basically, we can actually derive a lot more intuition from like basically just re-examining a convolutional neural network, instead of actually looking at the spectral features. And methodology-wise, this actually gives us confidence that the way to actually create equivariant neural networks is by actually focusing on it's basically by extending the architectures that has demonstrated some level of equivariance, from basically these kind of rotational equivariant MLPs to kind of these rotational equivariant convolutional neural networks. So what I mean here is this. So basically, I think the path towards building equivariant networks is not using a graph spectral methods, nor using algebraic equivariant networks. I don't have time to get into that, but those methods tend to have increasing complexity as you start to compose and start stack them on top of each other. So one of the prime candidates for as a viable roadmap is vector neurons. So vector neuron identifies the nonlinearities as basically the part that is actually rotationally non-equivariant, because the weight matrices are actually are linear operations, are actually rotational equivariant. So if you have a bunch of points you put in, and then you rotate all of the points according to basically the center of the coordinate system, its output is actually rotates the same way, except that you're not explicitly defining the output as basically vectors that also demonstrate, that also have this sense of rotation. But this is a linear operation, so it's actually abelian. So the core of computation is nonlinearity, right? The linear part just kind of rearranges things. So it's exactly the nonlinearity, the pooling layers and the activations that are actually not rotational equivariant. So this is kind of the framework we're working under, is that in order to actually produce equivariant, we will be looking at these key components in this computational graph, and then identify a basic, okay, so these nonlinearities and pooling layers are actually a part we need to fix. And vector neuron did this. This is from Dunn et al., the vector neuron paper from 2002. Okay, Sven, you have, okay, I should probably just I'll spend 1 minute on this and they'll be done. Okay, so basically
it was a question effectively, but I mean I can also ask it later.
Yeah, sure.
So the question is effectively like on that previous picture on the slide, like what's exactly the difference to the geometric deep learning picture? So in the sense, are you saying that you basically take different nonlinearities or allow for different nonlinearities than are usually taken in there? Because
yeah, okay, I'll address this question first.
Because the vector picture is kind of the same. Like that's something, you know, you can also embed into like a geometric deep learning framework, I would say. But you said more in the text in your words in the sense about the nonlinearities. With a certain
that's right. Yeah, that's right. Yeah. Sorry for going over time. This is pretty much the end of the slide. So, okay.
We started a little bit later, and you had a lot of questions, so don't worry about time. You can go 5 to 10 minutes more. That's fine.
Okay. Appreciate that. Thanks. Yeah. Okay. So there are like two branches of like a geometric deep learning work so far, right? Like in some sense, like I'm pretty new to this. This is kind of like what I'm planning on do like this quarter. So like it's like bear with me. So basically like after like a survey, what I found is that there are these like graph Laplacian methods that basically like look at like things that lives on the manifold and like basically use the diffusion operator to actually calculate like the eigenmodes of the entire manifold. So those are kind of like global structures, and one of the so we're looking at key tasks, like right, because like you're grounded on like solving a specific empirical task, and the key task here is basically shape correspondence. So like what they do is that they have this kind of like horse running around, and you need to be able to identify all the hooves like with each other because they're the same shape. So you can see that the task itself already has kind of like sense of locality and like coarse graining versus like, you know, of scale, right? But that's actually not in the like a graph Laplacian methods or the message passing methods. There's no like sense of scale. Everything's global. And then like the way that they fixed this, and this is kind of like the meta lesson I learned from looking at their work, is that they're like, okay, that's not good. Let's define local coordinates because on these manifolds, you don't have global coordinates. Parallel like transport doesn't work. So you define these local coordinates, and then it becomes like no difference. Like they're becoming no different from just a regular convolutional neural network. So basically, like doing pattern matching, I think, is the right way to go. Basically, yeah. So that's kind of like that side of things. And then the second side of things, basically the algebraic equivariant like neural networks. And I think like a bunch of folks in our field have have a really amazing kind of like theoretical work and like that has like a really nice empirical results on this. I guess like one of the challenges is that the complexity grows with respect to like basically like the complexity of the group like very rapidly. And like from my course of like a reading, it's not really clear to me whether like sort of like a stacked like a structures actually can scale to like basically like more complex problems. So like vector neurons kind of came in. This is not my paper, by the way. This is like a paper from Stanford. Came in like with a very simple like a scheme that actually solves basically this rotation equivariant problem on basically object-centric representation of point clouds. And it's so simple, and it's kind of like a problem formulation is like so precise that like I feel like maybe like extending like vector neurons to basically be able to do like a kind of like this kind of fine to coarse spatial graining is actually the way to go. So the thing specifically I'm trying to do right now is that like people already figured out how to use like vector neurons to learn basically object-centric like a shape embeddings or like descriptor fields basically. But the problem they run into is that it doesn't give you a way to actually represent things in terms of their parts. There's no like sort of like this differences in scale. So why don't we just kind of build like a convolutional like structures that actually works with this? So we want to basically combine like a continuous convolution with basically vector neurons and try to figure out ways to make it like an also rotational equivariant. I think it should actually be fairly straightforward. You just write like a tensor and one of the dimension corresponds to like the vector themselves, and that's it. But this is the kind of thing I'm looking at right now, and this is the reason why I'm choosing to go this way as opposed to going with the manifold learning, the manifold geometrical learning direction, or the algebraic equivariant direction. Yeah. More questions? Okay. Oh, and to respond to Eva, I haven't clicked on the paper, but I don't think I've seen that paper yet. Oh, interesting. Oh yeah, interesting. Yeah, I'll take a look. I've now seen. Thank you for this this recommendation. Yeah, I'll take a look. Where's my?
Thanks to you for the great talk. It is a timely example, so I'd be interested in what you think.
Thanks. Yeah. And the way vector neuron does this is very simple. They basically have the activations being a dot product between two vectors, and these output vectors actually rotates with the input data. So basically, if you just calculate the 2-point function between two of these vectors, then the difference between them is actually rotationally invariant. And if you do if you do a projection back to one of the vectors as a basic principal component, then a principal direction actually rotates together. So this is how vector neuron is able to get its rotational equivariance. Yeah. Okay. So basically, this is a radically different roadmap towards equivariance and symmetry from what I've seen before. It's also fairly new, and there are already recent works in robotics that actually uses these architectures to produce basically descriptor fields of for physical scenes. And it's very clear what is actually missing is that we need to actually have a way to build a hierarchy. This is the open problem right now in the subproblem domain. And then just to, I want to conclude the talk. Okay. And then I want to go over the roadmap. So the roadmap, the first step is to extend vector neurons to convolutional vector neural networks with the continuous convolution. And then the second thing is try to figure out ways to do deformable neural fields the same way that in pattern matching, sometimes it's helpful to actually have basically, for example, if you have a cup, all of the cup have one of the handles, right? But the handles can be different sizes and different shapes. Maybe by adding some kind of deformable transformation layer in between, that's actually learned, it could actually work. And then as soon as you start to do this kind of transformations as part of your inference, you're actually starting to do a localization. And localization is actually most of the time is a multimodal problem. So you cannot even actually learn it as a regression problem. Basically, there's not a one solution. There's multiple solutions. So the related works, there's implicit PDF, which got really popular. It's basically using implicit function to do explicit optimization to find basically the poses of a partially occluded object. As opposed to using regression to do that. So these implicit functions using a little bit like a search process as part of the inference process, I think that's an important step if you actually want to get deformable neural fields to work. And then a thing that can go parallel is basically we can do for scene synthesis, we can actually build geometry into the neural network so that we can actually aggregate information from two different viewing angles or different cameras densely within the network. So these are networks that can do multi-view synthesis basically by actually having some geometrical prior built in. And what could also work is basically trying to figure out new ways to look at a lot of these astronomical observatory data we have, and then try to figure out basically better ways we can design neural networks on top of what's already there, because we can actually specifically tailor them to the physics problems we're looking at. Okay, so that's it. Opportunities lies within robotics and physics, and new ways to represent information inside neural networks can make large impact. That's the talk. All right, thanks for listening.
All right, thank you very much. That was a great talk.
Thanks.
There were a lot of questions. If you have more, please raise your hand or just unmute yourself and ask. So while people are doing this, I have a question, and it's related to a question that was asked in the chat. I don't think you I think you missed it, or if you answered it, then I missed it. It's by the
I missed it.
partial. I don't know. So the question was, so on the reinforcement learning part, your explanation sounded very reasonable when you looked at the NTK and then at sort of seeing that the crosstalk was minimized by inserting the RFF layer.
Mm-hmm.
You had an example, I think it was called rotational hand or something like this, where it actually performed worse. Do you have any explanation for why it failed in this case? So why is crosstalk important? Or is there a way of seeing sort of when this would be detrimental of adding this layer?
Yeah, I think so. These results are gotten from like a RFF. It's not LFF. So we don't learn these layers. So but we're trying to make it fair. So we actually have like one less layer in our neural network. So the control experiment to do is to basically like, I need to look at the results with the learned for your features, and then need to look at the results with basically potentially one more like layers.
Yeah, no, I mean, so why is blue curve below in the bottom left finger turn hard?
Yeah. So one thing that we didn't control for is that, okay, so there are two things. One thing that we didn't control for is that here we replace one of the layers of the original architecture with ours, but we don't actually update that layer. So we're losing expressivity in some sense.
Okay.
And the second thing is that at the beginning of learning, there's a sparsity issue. So data is like much more sparse. So maybe the reason why we could sometimes perform like a worse initially, for example, here in the humanoid, could be that like humanoid is extremely high dimensional. I think I keep forgetting. It's like 78 dimensions here, because like in like Majoko domain, it's like 300 dimensions basically. It's like super high. Like maybe there's a data sparsity issue. Yeah. So those are my answers.
Okay, thank you. There's a hand by Sven. Is this a legacy hand or is it a new question?
No, it's a new hand.
Okay.
So you mentioned there's like the big open problem somehow addressing hierarchies. Can you explain a little bit more what you mean? And
yeah, sure. Oh, by the way, that work is ongoing. If anyone you guys like is interested in like this direction, feel free to reach out. There's also a way to actually do some kind of like a shape manipulation using like gradients, using like gradient operators defined on neural networks. It's kind of interesting. Yeah. Anyways, so the way that this works is the following. So like basically, you have input data which are points in the point cloud, right? And then there's a coordinate center for all of the point clouds. If you rotate all of the points with respect to this fixed center of the coordinate system, the output features here are going to like basically rotate together, right? Because this is a like a linear operation, and it's applied to basically each one of these indices. So, but what this relies on is that there's a center. So if the center moves, then like basically like these rotations will not basically rotate the same way anymore. It rotates with respect to different center. Does that make sense?
Yes.
So basically like you can think about this as basically like a global operator defined with respect to one particular like a coordinate system, but then like unless you actually limit the scale of this, for example, if I have a cup, this works for my cup. If I rotate my cup, it gives me the same like a descriptor, like a vector. But then if I but I want to be able to run this on like the handle of the cup and tell me that this is actually the handle of the cup. But then the handle of the cup actually rotates with respect to the center of the cup, not the center of the handle. So like my filter responses wouldn't be the same anymore. So you kind of want to like basically be able to like focus on the center and then like produce like a feature descriptor for that part And in order to do this, you actually need to like have explicitly like a sense of scale to like how the same way that like here it's almost like we have an MLP, but like you actually want to have a basically like a convolutional neural network, if that makes sense. Sorry, I feel like that's a long-winded explanation that's like probably not so clear.
So I think I get the gist of what.
Yeah. So this one only works for like object-centric point clouds. So you need to have a segmented point cloud that has like basically individual objects. And the reason why the object part matters is because the object rotates with respect to its center. There's a center for each one of the objects. If the center is moved, or like if you like look at smaller patches, it doesn't work anymore. And like people specifically in robotics are looking for ways where you can have like a kind of like ImageNet feature like things for like parts of the object. And that's currently like not possible. Yeah.
Yeah. Thanks. I mean, I can keep asking in a sense.
Yeah, feel free to ask. Yeah.
So the other thing, so you keep mentioning point clouds. So in what sense is it good to think about point clouds versus graphs? Because
I see.
Yeah.
That's a really good question. Like, do you want to finish answering your question? Sorry to interrupt.
Yeah, so the question is, right, because like obviously point clouds, I mean, there's slightly different architectures, slightly different approaches, right, to tackle both. And so,
yeah.
So like I hear you stressing point clouds, so I want to hear like, you know, what your motivation is behind stressing point clouds versus graphs.
I see. Like not particularly actually. So like the most important thing is that like there's shot noise. We work with discrete samples. And like basically in this paper that I took a lot of inspiration from, like when I try to understand basically why we should be doing pattern matching as opposed to like spectral methods, is that they work with these superpixels, which are basically sparse graphs, right? And then you get basically these discretization errors. And if I were to work with point clouds, I have to deal with discretization errors too, right? Because like the near field view I was trying to like basically push for is viewing everything living on continuous like vector space. Like the vectors live on the vector, like those like little like a bundles, like those like little fibers lives on like inside like this like vector space, right? So but you don't get dense samples, you just get some samples. And with LiDAR, it's even worse. Now you have LiDAR that's kind of doing this kind of like a scan that's like turning around like in the figure 8. So you don't even get like a nice grids anymore. Like so the way that they deal with this is that they just treat like give it a Gaussian kernel around each one of the points. And then like the sum of a Gaussian mixture is a Gaussian 2. So and then they can reorder basically the summation sign and the Gaussian error and the integral, and that's it. So basically, like when you work with discrete sample, you always have to basically like somehow denoise it a little bit. And basically, this is why I have the slides basically about like making convolutional neural networks equivariant again, where they look at the filter responses. These are classifications. If you just shift the like image a little bit, then the filter response actually changes, and you can look at the filter responses this way. It's not equivariant at all. There are all these artifacts. And then like Richard had this paper called Making Convolutional Networks like Shift Invariant Again. And they basically try to like change the pooling structure so that you're actually like doing the averaging after you are doing the pool, after you low pass filtering the activations and so on and so forth. And this actually connects directly back to like a wavelet domain image resolution using cycle spinning, which is actually a classical method in like a signal processing. And this is actually like from a paper called Translation Invariant Denoising. And this is why I think data augmentation works. So the way that like a cycle, like a denoising works is that you have a wavelet. So wavelet doesn't have like a well-defined like a spectrum. So you can't just low pass filter everything. So what you do is that you shift your input signal by like 1 bit or like 7 bits, and then you average like the transformed like results from the wavelet on top of each other. And this gives you so this is exactly what Richard did, but like basically people didn't connect this with these old methods. And this is also exactly what data augmentation does, except that you do that during training. So yeah, so like basically that's a very good question. If you want to work with data points, you care about like shot noise. And there are these like beautiful connections between like classical methods in like signal processing with wavelets and like basically what we need to do. Yeah. Any more questions?
Yeah, I mean, okay. So,
no, feel free to ask. I just raised it.
If they're raised hands, then so this obviously then also, like, if you're mentioning astro data on this slide, so that you know, you can apply there as well. So I guess you might want to work on a catalog level versus you know, working with the actual observations, right? If you want to analyze it. So have you thought about, you know, dealing with noise in those catalogs effectively?
I'm actually not super familiar with like the data format of these catalogs. I was more thinking about maybe like at some point it makes more sense to actually treat observations as like individual points with like some features, as opposed to like treating everything as basically image data.
Yeah, so basically these catalogs are basically like graphs effectively, right? So they are really
I see.
So there's no image data effectively. They are like graphs effectively. And they're super cleaned right from the collaborations. So that's you know, processed products, and you know, that's yeah. But that seems to, I mean, still you'll see some, you know, scatter in your clusters or whatever you want to cluster observations that you want to see. So that's why
I see.
Whether you I mean, the sample is
yeah, that's interesting. Like in like basically like a multi-dimensional scaling and like a spectral, like basically like a graph methods, the only solution is basically run Gaussian kernels through things. That kind of like makes you wonder, basically, maybe like some kind of like learned filters will work better. And maybe like you need to actually use some of these methods that like we just covered just now, which is kind of like taken from basically inspiration from recent like results in like computer vision, which is actually connected very tightly without actually like them noticing it, like from basically like a denoising like under the wavelet like analysis like a paradigm. Yeah. Oh, Yuslav had a question. I'll just respond to it real quick. So like your Slav, like that paper is accepted, but we haven't uploaded yet because we're like waiting on the key result for like, we want to claim that this actually reduces the value over estimation error. So like we already got it to work without like a target networks, but we're waiting for key results. We haven't put an archive yet, but you can actually find like an older version of this, which I'm not super proud of, on like open review. It's called overcoming the, let me just send it to you, overcoming the spectral bias of a neural value approximation. I'll send it to you. Give me 1 second.
All right, thanks.
Yeah. There we go. Yeah, that's the open review version. It's pretty old. We have more results now. Yeah, it's actually better if you look at our like a author's response. That one contains more results basically. Yeah. And someone else also had a question earlier.
I think you covered everyone.
Okay, cool. I think, yeah, okay, I'll copy like Eva's question because that one continues. Okay. All right, thanks for inviting me.
Well, yeah, it was a great talk. Thank you very much. Very enlightening.
Thanks. Yeah, I'm glad I ended up going over like a lot of things I didn't have time for during the talk, so that was great. Thanks for giving me a chance to sneak those in.